Hello, so now let's continue to learn the second part of the dot product 12.3. So this is called a projection vector. So now let's take a look. We have two vectors. So here we have u and the v vector, u vector and the v vector. And if we say u vector is p, q, and if we draw a perpendicular line, you can see if we draw a perpendicular line, we can get a new vector, so which is PR, okay? And we call this vector is the projection of vector u onto vector v. Now let's take a look at that definition. Definition 4. The vector projection of u vector onto a non-zero vector. So why we always say non-zero? Because non-zero has direction. We need a direction here. Non-zero vector v equals ps, okay, is the vector PR determined by dropping a perpendicular from Q to the line PS. From the point Q to the line PS. And let's take a look at the notation. So we choose the first several letters of projection, P, R, O, J, and then we say that's projection of U vector and onto V vector. So we call that the vector projection of U onto V. Okay, so this is notation. And then now let's take a look at how to find the projection vector. This vector is pretty important. You know, if, for example, when we learn the physics, if we move something, we have the force. Actually, we move this to the front, right, to the right side. We move this to the right. Actually, which force is the effective force? The projection of this force. So that's why we always want to find that vector. And let's take a look. The projection vector equals what? Of U onto V. We just look at our graph on the top. Okay, look at this graph. Now let's take a look. A vector equals direction times length, right? Direction times length. Or length times direction, doesn't matter too much, because vector has direction. Direction vector is unit vector, so direction is unit vector. We learned this in 12.2. Now let's take a look. How do you find the direction of this vector? I'm going to write another way, length times direction, a better way. Okay, length is like scalar times direction. Right. Okay, we are going to do this way. And then let's take a look. Length equals the length of U vector. This is the length of U vector. And here is theta. Theta is the angle between vector U and V. So you can see the length of PR vector, which is U vector times cosine theta. That is the length, right? Now, what's the direction? Direction vector, how to calculate direction vector, unit vector, that equals the V vector divided by its length. V vector divided by its length. Now we are going to combine. We are going to do this way. rewrite this. We are going to do u vector times cosine theta. We want to times another v vector length, okay, because we want to write this as a dot product. So it's going to be v vector length n times v vector divided by, we combine those two, v length square. And the numerator becomes u dot v by theorem divided by v square length, or v length square, and then times the v vector. Okay, so if you look at here, this formula, this is a scalar, because dot product is a number, length is also a number, so they both scalar, but this is a vector. So scalar times vector is still vector, right? So projection vector actually is also a vector, just has different lengths. Now I'm going to write down the formula again, write in better form. Projection of u vector onto v, which is u dot v over v length square and times v vector. This is how we calculate projection vector. Now let's take a look at definition 5. The number u times cosine theta. Actually, what is u times cosine theta? U length. So here's u length, u vector, v vector. U length times cosine theta is this length, right? It's called the scalar component. Because we know it's a length, so it's the scalar component of u in the direction of v. And here we have two formulas. Projection of u onto v, which is u dot v length square and v. And u length times this, actually just u dot v over v length. Okay. Now let's take a look at the example, how to use this formula to find the vector projection. Find the scalar projection. So when we read the problem, we need to know what it's asking for. It's asking for vector projection or scalar projection. So this is scalar projection. That's just the length of the projection. And this is the vector projection. It's a vector, right? Find the scalar projection and also the vector projection of the u vector I plus j plus 2k onto v vector, which is negative 2i plus 3j plus k. Okay, now let's take a look. We can find either one first, doesn't matter too much. Let's find scalar projection, that is u length times cosine theta, equals u dot v over length of v, by using the formula, the second one, the second. So u dot v, I'm going to write down in the component form. So 1, 1, 2, dot, negative 2, 3, 1. I like this way because it's a little easier to see. And the v length should be square root of 4 plus 9 plus 1. So let's do the calculation. So this equals root of 14. And the dot product is negative 2 plus 3 plus 2. So it should be 3 on the top. This is scalar projection. And the vector projection, that is u dot v over length of v by square it and times the vector v, so which is u dot v we already calculated here, so we don't need to recalculate. That is 3. And the length of v, that is root of 14, but here is 14, square it, right? Square of the length. So 14, and v vector is negative 2, 3, 1. Distribute the 3 over 14, so negative 6 over 14. Or you can simplify into 3 over 7 negative. So 9 over 14, 3 over 14. Okay, this is the projection vector. Let's try this exercise. U equals 6i plus 3j plus 2k, and v vector is I minus 2j minus 2k. So find projection of u over v. That means we're looking for the vector projection. So this equals to just the formula thing. Dot product is then the length of v and square it. So it should be 9, right? And the dot times I minus 2j minus 2k. Simplify. So it should be negative 4 over 9i plus 8 over 9j plus 8 over 9k. Okay, this is how we calculate the projection vector. Now let's take a look at next exercise. It's example in the book, but we don't want to do this as example. I think we can figure this out. So we have the force. We want to find the projection of the force. The force we know is vector. 5i plus 2j onto v vector, which is I minus 3j. You know, the good thing for the vector is before when we learn the force, we always just move horizontally, right? Horizontal or just vertically. But right now, because we onto this direction, that is the moving direction. For example, this vector, how to draw this vector? That is 1, negative 3. So this vector should be 1, negative 3, actually in this direction. And if we have particle, and we have force, the direction is 5, 2, so 5, 2 almost there. This force, and then we move in this direction. You know, so we can use any direction of the force, move on in any direction. So that's the good thing of the vector. So let's take a look at this problem. Here, projection of the force onto the vector v, which is just a dot product length square times v vector. And here, those are two vectors just in 2D. Dot product should be 5 minus 6, so it should be negative 1. And the v length square, so it should be 1 plus 9, should be 10. Okay, and then times I minus 3j. After we simplify, negative 1 over 10i plus 3 over 10j. That is the projection vector. Next, let's take a look at the application of the dot product. Why we want to learn dot product? firstly, let's just draw a graph of the force. So we have something like we have an object, okay, and we have force here, vector, and we have displacement, this also vector, okay. Displacement is vector too. Here I just draw the horizontal, right? But you know we can also have this force and any direction displacement. So here, just for easy to see, we just draw this way. Okay. Right now, let's take a look. What is the work? So we use W as the work to express the work. Work equals what? Okay, the work done by the force in the direction of D, so which is actually F times the cosine theta, which is the projection, scalar projection here, right? And we know this, we have this amount of force, and then we times the length of displacement D. And in another way, we can just write down this as dot product, F dot D. Okay, so in the future, you know, we can just write down, use our formula how to find the work. So let's see, W equals F dot D. This is a more general formula, okay, because D here can be any direction. It's not just horizontal direction. Now let's take a look at definition 6. The work done by the force, and here is constant force. In calculus 4, you will learn variable force like a function acting through displacement, and the displacement is given by D. Okay, yes, W equals F dot D. Now let's take a look at our example 6. If the force of length actually is magnitude of the force, which is 40 N, and this is displacement magnitude, which is just a length, right? Length. There's no direction, and the theta is 60 degrees, and the work done by F acting from P to Q is, okay, W, oh no, sorry, work is not vector. Okay, work equals F dot D. So by the theorem, we know that is F length, D length, and the cosine theta. In this case, F length is given 40, D length, which is 3, and the cosine, the angle is 60, so it should be pi over 3. Okay, so the final answer should be cosine per 3, which is 1/2. After we simplify, 60, and here's J. That's the unit. Now we can take a look at the exercise problem. Actually, this is the homework, kind of homework problem. And here we know our F is 5I. Okay, so the graph is not given. Here I just give you the graph. And move the object from 0, 0 to 1, 1. Something like that. So here we have object move to 1, 1. So this is our displacement, right? And the 5I, which is here. 5I means only has component, S component, so J's component 0. So the direction should be just like a 5i, so it should be like the point 50 here. Now let's see. Okay, so for this problem, the D is now given, the dot product is now given, so we have to calculate everything by ourselves. So let's take a look. If we have the graph, there are several ways to do this. I'm going to show you the way I like. So from 0 to 0, firstly, we can see what is the angle, 211. So it should be easy to tell it's power 4, right? That's the angle. And so the work just equals F dot this one, and then we use the length, D length, cosine theta. So cosine theta is power 4, and the length of 5i is just 5, and the length of D. So length of D, so should be length of here. And if you look at the length, do you know how to find the length here? Because the point is 1, 1, so here should root 2. That is our length of D, right? So the other way, you can find the actual D vector. So I can show you another way. N times cosine power 4 here, 5 root 2 over 2, and actually they cancel, the D become 1. So the final answer is just 5. Okay. We can say this is the method 1. So the other method 2, okay, we can find the D vector. So actually, what's the D vector? Oh, this is the D vector is even better. Okay, this way. D vector is just 1, 1. Is that right? Because the start point is 0. Its origin 0, 0. So F is given. So that work just equals F dot D. So which is 5i. So it should be 5, 0. And dot 1, 1. If we calculate 5, 1 plus 0 times 1, which is 5. So you can choose either way to calculate this problem. They all work. So we just need to know how to find the work. Just a dot product of the force and the displacement. And then, by using the vectors, this is a vector in 2D, right? In 3D, our F can be in any direction. Our D can be also in any direction. So we can move, the object from one position to another position. For example, given P and Q, we know how to find the PQ vector. So that is our displacement vector, PQ vector, move from P to Q by using terminal point minus initial point, and then just dot the force. So it's so easy to find the work by using the vector way. So this is the application of the dot product. And in 12.5, we are going to learn more applications of dot product. And 12.5 is combination of dot product and cross product. So in the next section, 12.4, we are going to learn cross product. Okay, it's very useful thing also. We can stop here.